topic of lecture 4 is regression discontinuity and kink designs. Regression discontinuity has been around for quite a while now and is considered one of the most effective methods of causal inference. It obviously can only be applied in certain contexts, but when it can be applied, it's a very transparent method, and that's why it actually is so popular among researchers. So the identification assumptions that we need to make in a regression discontinuity design are easier to defend than, for example, in a standard instrumental variable approach. In the first video, we're going to cover the basics of regression discontinuity designs. So the starting point here is that we want to estimate a treatment effect. So we want to estimate the effect of receiving a treatment on the average outcome of a population of interest. But we have this problem that the key identification assumption doesn't hold. What's the key identification assumption? It's that basically the treatment is assigned as good as randomly, such that the potential outcomes of those receiving the treatment and those who don't are the same. But that's the identification assumption that we need to make in order to claim that our effect is causal. Now, what is this first expectation here? This is basically a counterfactual. This is if those people who took the treatment had not been treated, what would have been their outcome in that case? And that counterfactual in a randomized experiment in expectation should be the same as the outcome of those people who actually weren't treated. So that's these guys here. And that assumption, as we've seen before in the course, hardly ever holds unless we run an experiment. And that therefore we need to apply other techniques where we can be confident that that assumption holds for parts of the population. So we've learned already about techniques such as instrumental variables, and regression discontinuity is another technique that does exactly that allows us to estimate a causal effect because it picks a part of the population, or it applies to a part of the population where that assumption holds. So what does a regression discontinuity exploit? It exploits typically arbitrary thresholds that determine the treatment assignment. Right? So in many laws and regulations, you have thresholds. So people whose income falls below a certain threshold get more support. I show you here a few examples. So that's the income threshold of social benefits. Or in schools, if the cohort size is above a certain threshold, they split the classes. So they would have up to 30 students, they would have one class, but if the cohort size is 31, then they split the class into two. That's an arbitrary threshold. There's nothing natural about that threshold. Or think about GPA thresholds for getting into college. Right? So if your CAO points in Ireland are above a certain threshold, you can attend a certain course, and if you're below, you cannot. Or there are many countries that have specific procedures for treating newborns depending on the birth weight. So if the baby is below 1500 grams, which is really low, then a special treatment kicks in immediately after birth. If the baby is just above that special treatment does not kick in. Why can we use these thresholds for estimating causal effects? Well, we can do this under the assumption that the units that are just above and just below the threshold, that assignment of being just above and below, that is as good as random. So those units are pretty much the same. That obviously depends on whether units can select into being above or below the threshold. But for example, when it comes to GPAs or when it comes to the treatment of babies and babies' birth weight, that is obviously pretty hard to manipulate. Right? So you cannot really manipulate as a parent whether your baby has 1,503 grams or 1,497 grams. So the idea here is that this rule, this discontinuity, assigns the treatment, but at that discontinuity, nothing changes. Nothing else changes. And so if that's the case, then we can estimate the effect of any of those discontinuities on the outcome. Right? So we can, for example, look at the effect of a student's class size on their education outcomes, or we can look at the effect of receiving more generous social benefits on all sorts of outcomes, and so on. Now, RD has become its own little subfield in causal inference, with lots and lots of methods papers coming up in the last couple of years refining this method. So if you use this method, or even if you read papers that use this method, you have to get used to the lingo. So we have two elements here that are often referred to. One is the forcing variable. So that's the variable that determines treatment assignment. And it's sometimes also called assignment variable, or just assignment, or it's called running variable. So in the example of baby's birth weight, but that's the birth weight, that's the forcing variable. So the baby's birth weight determines whether the baby is assigned to treatment, which is, an emergency procedure in the hospital where they get special support, or not. And then the discontinuity is the threshold value at which the treatment assignment jumps, either from 0 to 1 or the likelihood of being assigned to treatment jumps. So here's just a graphical example of a linear regression discontinuity design and how that typically works. And so we want to know the treatment effect, which is this effect here, and we have an assignment variable x, and then at the discontinuity c, we have that jump in the assignment variable. And so think about it as, if your income increases a certain threshold, or if you, in this case, probably the best example would be a GPA. If your GPA from high school increases a certain threshold, you get into a better type of college. And then the question is, does going to a better type of college increase your earnings? And so if we observe data like that, where those who had a GPA just below the threshold have significantly lower levels of earnings than those just above, but then we can attribute the difference to the fact that they actually went to a better college, right? Because it was as good as randomly assigned, because we compare here people who had a GPA that was just above the threshold to people who had a GPA that was just below the threshold. That's the idea behind a regression discontinuity design. There are obviously lots of things we need to think about. To what extent does that jump? To what extent is that jump real, or is it just a statistical artifact? How big is that jump really? To what extent does it depend on the functional form, to the slope of those lines and the shape of those lines? Should they be linear? Should they not be linear? And so on. So there's lots of things to think about, but that's how it works in principle. And we have to distinguish here between two types of regression discontinuity design. So the first one is a sharp design, which is what you see here with the dashed line here. So what happens with a sharp regression discontinuity design is, if at the discontinuity the probability of getting treated jumps from 0 to 1. So everyone gets treated at that discontinuity. And I will show you examples for such that are sharp regression discontinuity designs. However, one that is more common is fuzzy regression discontinuity designs, which is the more general case where the treatment probability jumps in general, but it doesn't necessarily jump from 0 to 1. The example of the emergency procedures for babies is probably a good one here. It's not that babies whose birth weight is just above the threshold do not get treatment in the hospital at all. They're just less likely to get this special treatment where, you know, doctors do lots of additional tests and the mothers get some support and so on to make sure that the baby really has a good start into life. Babies above the threshold may get that treatment as well. They're just less likely to. And so that the likelihood of getting treated jumps at the discontinuity. And those two types of regression discontinuity design, you can basically see them through the lens of an instrumental variable estimator. The sharp regression discontinuity is basically like an IV with perfect compliance. So you cross the threshold and your treatment probability jumps from 0 to 1 or from 1 to 0. With a fuzzy regression discontinuity, you have imperfect compliance. So the treatment probability jumps, but it doesn't jump from 0 to 1. It's just the likelihood of getting treated is increased. So basically, the fact that you cross the threshold, that's as if your instrument jumping from 0 to 1. But then whether people actually take the treatment, well, all that we need is that the people who were encouraged to take the treatment by the instrument, by crossing the threshold, have a higher likelihood of taking the treatment. Now here's an example of a sharp regression discontinuity design. If you believe economics is called the dismal science for a reason, here is why. Okay, so we're talking here about deaths of young people in the United States. And what you can see here is that around people's 21st birthdays, you see a spike here in the number of deaths. And so what we see here is that the average number of deaths on a given day of people right before someone's 21st and 22nd and 20th birthday. And we see that obviously this, due to sampling variation, it hovers, but there is this noticeable spike at the 21st birthday. And that's obviously interesting. So what could be behind this? If this is the States, well, what people can do in the States after the 21st birthday is they can actually drink legally. They were already allowed to drive at age 18, or in some states even before that, but 21 is the legal drinking age. And so what they study in this paper is the effect of being allowed to drink legally on deaths, on the likelihood of dying. Yeah, so and that's obviously a very it is an example of a sharp regression discontinuity design. I mean, here notice that whether it's sharp or fuzzy depends a little bit on what the question is. If the question is what is the effect of being allowed to drink, then it's a sharp regression discontinuity design, because that by law just changes from not being allowed to being allowed on the 21st birthday. However, if the question was rather, what is the effect of actually drinking on the outcome, on the likelihood of dying, then that's obviously that would be a fuzzy regression discontinuity design, because it's not that no one would have drunk before and people would then start drinking right after and everyone would do so. But what we can expect is that there is a jump in the likelihood of drinking. But here the question is not about whether people drink or not. That the question here is basically like a reduced form, which is whether people are allowed or not, and that is assigned by this function, which is if your age is above 21 or on your 21st birthday and later, you're allowed to drink. Before that, you're not allowed to drink. Right? So in that case, the treatment status is a deterministic function of the running variable. So we can put this then into a simple regression framework and actually estimate that the jump at the discontinuity. So how do we do that? Well, we relate the outcome variable, the death rate, to the treatment, which is whether someone is allowed to drink or not, and control for age. Yeah, so we control for the running variable, and then we have a dummy that equals 1 when the person is above 21 and 0 if below. Yeah, and then we can clearly see that there is a jump here, and the parameter rho, that parameter quantifies how big that jump is. That's in a nutshell how the regression discontinuity framework works when we actually do the inference based on a regression. Now, what we always have to ask ourselves is, are the assumptions underlying the regression discontinuity fulfilled in a given context? So we can, so only then does the estimate we're getting here for rho represent a causal effect. So the most important assumption is that there is no selection into treatment, so and that nothing else changes at that discontinuity, right? So in other words, the treatment should be solely determined by the running variable, but by nothing else. And that's plausible here because people can't pick their age. They can maybe forge the birth date on their ID card. That maybe they can do that, but they can't really change their age. Okay, and so it's not possible that anything else but the age determines whether someone's allowed to drink or not. Once again, be careful here. This is not about whether people actually drink or not. The question here is, are they allowed to drink or not? And so that's what we can do here, and we can have a plausible causal effect of being allowed to drink. That is this parameter rho. And you can look at their paper to see what else they're doing. You know, they're then looking at different types of deaths, road deaths, and so on, and see what lies behind this. Is it that more people die on the road, or is it that people die elsewhere? It turns out it's mainly driven by people who drink and then drive. And here you can already see the advantages and disadvantages of regression discontinuity designs. So the advantage is that regression discontinuities are, if done well, credible and transparent, right? It's oftentimes hard to explain what an instrumental variable estimator really does to anyone who is not an econometrician, and as in to most people. But if you show them a picture like that and say, look, you know, below that age threshold, the probability of dying is this, above it's that, and nothing else changes, that's something that you can even show to a policymaker and who is not familiar with the technique. and still provide some, and they will probably understand what you're doing here. So that's a huge advantage, the credibility and the transparency of that research design. But there is also a downside to it, which is that you can obviously only estimate a local effect. So with this study, we can say nothing about what would happen if let's say 50-year-olds who are currently allowed to drink would all of a sudden not be allowed to drink. We don't know anything, not even about, or we couldn't say anything about 18-year-olds or 16-year-olds. Most likely the effect would be similar, but then the further we go away from that age threshold, the harder it gets to plausibly extrapolate. And that is the downside of regression discontinuity. So it's basically, it works like a localized experiment. It's not an actual experiment, but it exploits a local natural experiment, but we cannot say much about what happens then away from the discontinuity. The current methodological research is trying to find ways to extrapolate. That's where the literature is currently heading. But obviously, when you exploit the single discontinuity, that is not so easy.